Dad, how did this get here? Didn't we just order it like a few hours ago?
When my older daughter asked that, I stopped for a second because it is a simple question with a surprisingly deep answer. Somewhere between a tap on a screen and a box on our doorstep, invisible systems spin up, data races across networks, decisions get made in milliseconds, and the physical world moves. It's fascinating to think what happens when you stream a song, book a hotel room, reserve a flight, or open an app and just expect it to work. All this technology is so fun, and I love working in this industry. I've spent my career building software and systems that make up the internet. I was CTO at Shopify and ServiceNow, an SVP at Slack, an early engineer at Cisco Systems, and now I'm CTO at Webflow. I've helped build data centers, protocols, software, and services, and led global teams along the way. This podcast is for anyone who wants to understand how our modern world actually works, not just shopping and delivery, but the invisible machinery behind nearly everything we do. It is for anyone who's ever wondered, how did this get here? Or how did that actually happen? I'm excited to take you on a journey, to take these layers of technology apart and explain them in a clear, grounded way. You probably think you connect to Wi-Fi, you're on the internet, and away you go. Well, I wish it was that simple. I'm Alan Meinwand, and welcome to Pixels to Packages. Hello, everyone, and welcome back to Pixels to Packages. I'm Alan Meinwand. I have to tell you, I have been looking forward to doing this episode since I first came up with the idea for this podcast. This episode is about something I have truly loved for many years, the technology behind routing. Routing in the sense of moving packets across networks, and routing in the sense of moving physical boxes from warehouses to trucks to airplanes to your front door. Those two things are far more similar than most people realize, and I've always loved the systems and the algorithms behind them. You see, when I started my career, I remember sitting at my desk at HP on a Saturday morning, helping install a network connection to our buildings in Singapore. I barely knew where Singapore was on the map, but I understood how routing worked from my cubicle in Palo Alto on our Class A Network 15 to the new subnet that had just appeared in the IGRP routing table. I knew the links. I knew the routes that appeared in the routing table in the Cisco routers. How those Cisco routers in a data room a few feet away from me behind a glass wall had run those algorithms and had those routes appear. And how those routes allowed my TCP/IP connection, using an old tool called Telnet, back in the days before SSH, to connect from my machine to a router in Singapore. It felt like pure magic. And honestly, it was just the coolest thing ever. And to me, routing still is the coolest thing ever. When we first talked about packets back in episode 1, we sort of simplified the story because you really have to. You can't dive into all the details of the entire networking technology stack in a 20 or 30 or maybe even 500-minute podcast. But you'll recall that data gets broken into packets. Packets move across networks, and eventually those packets arrive somewhere else. In the same way, packages move through warehouses, trucks, aircrafts, ports, sorting centers, and eventually shows up at your front door. And over the last several episodes, we've talked about both of these worlds. We talked about what happens when you open your browser and click on the buy button. Your laptop generates data. That data gets wrapped in layers of networking protocols. Packets move through your home network, through your Wi-Fi, through your internet service provider, across fiber optic cables and backbones, into data centers, and eventually a web server responds back to you through that HTML and through HTTP, that protocol. And in the last episode, we looked at the physical version of the same idea. When you click buy, inventory systems wake up, warehouses coordinate fulfillment, forklifts move pallets around giant buildings and warehouses, trucks move cargo between regional hubs, aircrafts move freight overnight, and eventually that package shows up at your front door. That world of commerce is what connects the pixels to the packages. Now, if you haven't listened to the previous episodes, I'd actually recommend going back right now and doing that, because this episode builds on all of them. And there's 5 episodes before this that I think are really, really useful and informative if you keep listening here. But if you want to jump right into episode 6, let's do it. In all those conversations that we had, In all those previous episodes, we skipped over one of the hardest and most interesting parts of the entire routing system. Not what's actually moving. We talked about packets and packages. That's actually the easy part. The really interesting question is how to figure out where those things go in the first place. How do they move? And that's what routing is about. And once you start understanding routing and paying attention to it, you realize it sits underneath almost every modern system that we depend on. The internet depends on it. Logistics networks depend on it. Cloud computing depends on it. AI depends on routing. Commerce depends on it. Transportation systems depend on it. Routing is basically the invisible intelligence layer underneath all the modern infrastructure. It's part of the system that is constantly answering one deceptively simple question. And this is the one question that everything always sort of comes back to in routing. Where should this thing go next? Where should the packet go? Where should the package go? Where should the pixels go? And it turns out that question is so much harder than it actually sounds. Because while you can think about where to send the thing next, the world is always changing underneath that system. Networking links fail. Roads close. Warehouses fill up. Storms and weather disrupt transportation. Demand spikes unexpectedly for a new item or a new piece of content on the internet. Hardware breaks. Chips and fiber and cables, they wear out over time. Fibers get cut. Data centers overload. Power systems go down. Trucks break down. Aircraft get delayed. And somehow, these systems, these routing systems, continue to adapt in real time without any single machine or organization fully understanding the entire network end to end. That's the fascinating part because these systems aren't centralized. They're the largest distributed systems you could think about. And that's exactly why they scale to the size of everything that happens on the planet. If it was one big centralized system, it'd be really hard to maintain, control, and operate. So in this episode, we're going to spend some time inside the routing layer itself. We're going to go look at how the internet decides where the packets go, why local and global routing are completely different problems, and why the best route is sometimes not the shortest route. And one of the best ways to understand internet routing is to sort of compare it to physical package delivery, the mail system, which feels a little ironic because we're using old school snail mail systems to explain one of the most advanced technology systems humans have ever built. But the analogy works pretty good. See, every packet on the internet, as we talked about previously, contains a destination IP address, just like every envelope or package contains a street address. At the most basic level, routing is simply the process of figuring out how to move something from where it is now to where it needs to go next to get to its final destination. But what makes this so interesting so quickly is how much information different parts of the system actually need in order to make that happen. Thinking about the postal service, the mail service. Inside a local town, your postal office, your mail carrier, probably knows the streets in pretty good detail. They know which neighborhoods are difficult during rush hour, which apartment complexes are annoying and have hard door access, which roads are most efficient, which lights are timed, which routes save time during different parts of the day. These are routing decisions that are highly detailed and very local. And that's a lot like what happens inside of a single organization's internet or network. Inside a company or a cloud provider or a university or an ISP, routers typically use something called an Interior Gateway Protocol, or IGP. There's a protocol called OSPF, Open Shortest Path First, or ISIS, Intermediate System to Intermediate System. These are, again, some of the alphabet soup we get to deal with in this world of technology. But these are basically protocols that allow routers to communicate amongst each other and build a detailed shared understanding of the network closest to them, the streets that are closest to them that they're connected to. Routers exchange this information with their neighboring routers. So every router is connected to another router over fiber or cable or some sort of microwave link or some sort of other connection, wireless link. And what they share is where they are connected to
the bandwidth which they can get there, how reliable they are, and something called cost. Think of it as like every post office telling every other post office what roads are between them. Are they highways? Are they dirt paths? Are they normal streets, etc.? And then there's this thing called cost. And cost is important because it doesn't really mean physical distance. Because it could be faster to take a highway 20 miles than it could be to take local side streets 5 miles. So cost might represent latency, time, congestion, utilization, reliability, or some other operational preferences defined by network engineers. This definition is something called traffic engineering. See, a path that is geographically shorter may actually be avoided because it's congested or expensive, while a longer path may perform better overall. So routers exchange information using this interior gateway protocol about the paths they know about and the cost of each of these paths. And when they exchange this information, they build something called the link state database, which is basically a synchronized map, a tree of the local network topology. Not the whole internet, because that would be really, really hard. Just their own little part of the world. Going back to the mail analogy, just their own town or just their own city. And once routers have that topology, each router independently calculates the best path to every destination using something called the Dijkstra algorithm. It's just a way to figure out the best way to get from where I'm at right now, from my local post office, from my local mail route, given the knowledge I know about the routes and the cost and the roads to each of those next hops for this letter or for this packet, what is the best way to go? Inside of a corporate network, these destinations might be individual portions of a route called subnets, representing buildings or floors or data centers or regions or Kubernetes clusters or campuses. You might see things for routes like 10.42.17/24 or 172.16.88.0/21. These are IPv4 routes. They represent a portion of a particular network, sort of like a zip code or a portion of a city. And someday, perhaps I'll do an episode on just IPv4 and IPv6 routing and how those addresses represent both a region and a specific address at the same time. It's sort of like how the address on the envelope has both the street address and the city and the postal code. You can see that inside of every IPv4 and every IPv6 route. Now, in a reasonably large enterprise network, an internal routing table may contain a couple hundred of these routes. And a very large, internet service provider background might be thousands or tens of thousands. But fundamentally, when these routers exchange this interior gateway protocol and build this set of routes that each have a cost, that cost could be a variety of things, it's a detailed local map. It's like a city delivery system knowing every neighborhood street and every local delivery route in detail and the cost to get there. And once the packet needs to move between cities or countries, the model changes. We're going to talk about that in just a second. So think about packets inside of a local network, inside of a given provider's network, having a very detailed tree, a very detailed map with costs to know how to get from where you are right now, from where the router sits in the network, to the next hop for that destination. The best way to think about it is every router, just like every post office, is making individual decision based on what it knows about the map right now and the cost to every single path and routing those packages or those packets down that path. Now, once a packet or package needs to move between cities or countries or between networks, the model changes a bit and routing gets a little more complicated. This is because like a postal sorting facility here in San Francisco doesn't need to know about every street address in Tokyo or even in San Jose. That would never really scale. If you imagine every street address on the planet changing and every post office needing to know that all the time, it would be super hard. Instead, what the local postal facility or the local router needs to know is how to move the packet or the package towards the zip code or the next region, in this case, towards Japan. So it routes that based upon a zip code, regional hubs, cargo airports, custom gateways, all sorts of things like that. And it's only once the package gets close to its final destination does the routing become highly detailed again. So if you think about it, a mail letter going to Tokyo, starting here in San Francisco, the post office here in San Francisco doesn't really need to know much about Tokyo. Just needs to know Tokyo is in Japan at this postal code. And then thinks, okay, in order to get to Japan at this postal code, I'll send this to the airport. And then the San Francisco airport needs to send it to the airport in Tokyo. The airport in Tokyo needs to figure out how to send it to the closest mail hub to where the letter is destined. And that local mail hub then has that detailed map, that interior gateway routing algorithm to figure out how to get to the street address. And the internet works almost exactly the same way. Inside networks, routers use that detailed local topology information, that interior gateway protocol, that Dijkstra algorithm, that tree of knowledge. But between networks, the internet uses a completely different protocol, because why not, called BGP, or the Border Gateway Protocol. And one of the most important things to understand about the internet is it's actually not one giant network. It's thousands and thousands of independently operated networks connected together. Internet providers, cloud platforms, mobile carriers, governments, universities, they all run their own infrastructure and make their own routing decisions. These independently operated environments are called autonomous systems. So autonomous system is a group of networks, and it's assigned a number. And BGP is how those autonomous systems communicate reachability to each other. It's sort of like saying Japan advertises to San Francisco or advertises to the US, I can get all the stuff in Tokyo, and I can get all the stuff in Narita, and I can get all the stuff in every city in Japan. It's not like every post office in the United States needs to know about every single city in Japan. Just needs to know to get to the region called Japan, send it to an airport, and that airport knows to head towards Japan. That reachability is most important. Now on networks, they might advertise a range of IP addresses, basically saying, if you want to get to any of the destinations in this range, send it to me. A little more technically, a provider might advertise something like 203.0.113.0/20, or an IPv6 allocation, which has a much larger number that basically tells its neighboring routers, I know how to get to everything inside of this block of addresses. Sort of like Post Office A telling Post Office B, I know how to get to everything inside of this zip code. Or like the post offices in Japan telling the post office in the United States, I can get to everything in Japan. That aggregation is so critically important because it keeps the internet stable. Again, imagine if every post office everywhere on the planet needed to know every single street address. Well, that wouldn't scale. Similarly, if every router on the planet needed to know how to get to every single IP address, that doesn't scale. If every home network, every office subnet, every cloud cluster, every mobile carrier, every Wi-Fi on Earth had to be individually listed in a global centralized routing system, that wouldn't work. That's what I'm saying. There isn't a centralized system here. It's a large distributed system. That centralized system, if we had it, means routers would collapse under the sheer size and constant churn because things are always changing, right? Weather's changing, links are changing, networks are being brought up, traffic conditions are changing, costs of those links are changing. So global routing intentionally extracts the world into regions, very similar to how postal systems use zip codes and regional sorting hubs. This is long before anyone really needs to worry about how to get to exact street addresses. And even with that abstraction, even with that summarization, even with that aggregation of addresses into zip codes, into autonomous system numbers, the scale is enormous. The public BGP routing table right now contains over 1 million routes globally. And the IPv6 table is continuing to grow as well. Every major internet backbone router on Earth has to continuously process those routes, apply those policies, understand the failures, recompute forwarding decisions, what's called convergence, and keep traffic flowing in real time at millions and millions and millions of decisions every second of every day. And unlike interior routing systems, no single route on the internet has a complete map of everything. When you're inside of a network using that interior gateway protocol, you do have that tree of everything inside your network, like being inside of a city. But as soon as you get outside that region and you get into BGP world, no one has a complete map of everything. Every network only sees partial information based upon what the neighboring networks chose to advertise. Again, think of it like the post offices in Japan only tell the post offices in the US, I can get to all this stuff in Japan. And they don't talk about every street change, every address change, every road change, every weather event. And this is one of the reasons the internet and routing is just so fascinating, because no single machine actually understands the whole system, and yet it somehow still works all the time. And that's a really, really important idea, because routing is fundamentally, again, happening one packet or one package at the time. The question is, where does this data or where does this package need to go next? That's the question that the routers are asking. That's the question the mail carriers are asking. That's the question the people delivering the packages are asking. And then depending on if they're in the local city using that detailed map, or going between regions or sorting hubs using the border gateway protocol or using those aggregates, that's the answer to the question. Every individual IP packet contains a destination address, and routers examine that address and decide where the packet should go next. They don't actually look at the connection. They don't actually look at the application. They don't make a decision necessarily on this is an AI query versus a website versus an email. They look at each individual packet. It's that IP layer of encapsulation we talked about a few episodes ago that hides the rest of the data in the packet that allows the routers to make the decision. Similarly, if you mail a letter between two locations, people don't look inside the letter and say, well, this is a personal letter, so we'll route it this way, and this is a bill, so we'll route it that way. They look at the address and the zip code and the country code, and they make those aggregate decisions along the way. So you remember your browser doesn't really want these packets showing up in random order. Because if you think about it, if every router for every packet is making individual decisions, they're sort of all routing across the world very, very quickly, and they could end up out of order. And you recall from a previous episode, this is where the Transmission Control Protocol, or TCP, comes in. TCP sits above IP, takes all these independent routed packets, reassembles them into a reliably ordered connection stream. TCP tracks things like sequence numbers, finds if packets are missing, looks for lost data, manages the congestion, the flow between the source and the destination, and it creates an illusion of a stable connection between the two systems. So IP is responsible for moving packets constantly through the network as the network changes, as the interior gateway protocol changes topology inside the network, as the border gateway protocol changes topology between the regions. TCP is responsible for turning those packets back into a stream that's coherent and reliable, that is delivered up to your browser or delivered to your chat application or delivered to your mobile payment or whatever it is. And all this is happening so amazingly fast. Just take a step back for a second. You open a browser tab. Domain name system, or DNS, resolves the name into an IP address. That was a bunch of packets going back and forth just to get you that. TCP establishes a connection to that destination IP. Thousands of packets begin flowing through switches, routers, fiber optic cables, load balancers, firewalls, data centers, back and forth. These packets may traverse multiple providers, use information from the IGP and the BGP, multiple cities, multiple countries, dozens of independently operated networks before they ever arrive at their destination, and the responses come back. The packets might arrive slightly out of order. TCP puts them back together. Packets might get retransmitted because they're missing. Congestion windows flow, buffers fill and drain, routing tables update, traffic shifts around failures. And all of this is happening in millions of seconds, every second of every day across billions of devices simultaneously. And routing is just fascinating. You get the algorithms inside the network, you get the algorithms between the networks. Again, it's a lot like snail mail. You get the local city topology that the mail carriers and delivery people know. You get the hubs and the routing between countries based upon postal code and city code. It's just so cool and so analogous how all this works. And many people never see it. They don't even grok that it's happening. They just see a web page load. And that's what makes the internet still feel so magical. After working in this technology for many, many years, I am still fascinated by underneath every click is this enormous distributed system that's coordinated and operating at an extraordinary speed. And the fascinating part is the network is constantly changing underneath all of it. A fiber optic link fails, traffic spikes, a router disappears, it fails. A new circuit comes online, a new path shows up, and a new cost, and a new part of that graph. A data center region becomes overloaded, a provider changes a route, decided to change their policy. And when that happens inside of a single network, routing protocols, those IGPs, detect that change almost immediately. Routers exchange updates, they tell about the costs and the path and the policy changes. That Dijkstra algorithm, that forwarding table gets rebuilt, and traffic dynamically shifts onto alternate paths. Most users never even notice this is happening. Matter of fact, as you're listening to this podcast, it's happening just to carry the sound of my voice to you. And routing is reoccurring and changes are happening right now. Underneath what we're doing right now, you listening to this audio or watching this video, thousands of routers may have just recomputed forwarding decisions across an entire network in real time. But the subtle thing people misunderstand is that, again, the shortest path, the routing path, does not necessarily mean the geographically shortest path. Routing is really about optimization under constraints. Because a geographically longer route may perform better because it has more capacity or lower congestion. A lower latency path may be avoided because it is overloaded or operationally expensive. Routers do many, many techniques, something called equal cost multipath to look at if you've got router A that's trying to send packets over to a destination network and it sees multiple paths that have the same route. It'll actually load balance those packets across those different routes using equal cost multipath or ECMP. And different traffic flows may traverse different links entirely. So even inside of a single network, routing is highly dynamic, decentralized, and continuously adapting. But things even become more interesting, as we've talked about, once traffic leaves that private network and goes across the broader internet. Because while the United States knows to go to Japan over a given route, it doesn't always say, what is the shortest path? What is the geographically shortest path? Also on networks, the Border Gateway Protocol doesn't say what is the shortest path to reach the autonomous system, that group of networks. What it really asks, both in the pixels, the packets, and the packages world, is which route should I prefer given my policies, my business relationships, my performance goals, and any operational constraints. That happens in the physical world, that happens in the internet world. And that's one of the more important ideas in internet architecture, this idea of what's called traffic engineering. The best route on the internet is often determined as much as by economics and policy as by algorithms and real engineering. Maybe one provider charges less for moving data from point A to point B. Maybe another has a congested network. Maybe traffic needs to remain inside of a geographic region for regulatory reasons. You want to keep it inside a specific network as long as possible for regulatory security reasons. Maybe a cloud provider wants to keep traffic on its own backbone because it thinks that its network performs better than handing it off to someone else. And as a result, internet traffic often takes paths that seem strange from the outside. Traffic between nearby cities traverses in another state or another country. A lower latency path might not get used because the economics just don't support it. One provider may intentionally avoid another provider because of disputes or policy decisions. And at a global scale, routing starts to look a little bit less like GPS navigation and more like international trade agreements. And that's what makes the whole thing remarkable, that it actually really works. Because despite the fact this is decentralized, despite the fact we have incomplete information, we have business constraints, we have hardware failures, we have weather, the internet still functions incredibly well. You can really appreciate this when you think about what happens during failures. So imagine there's a major fiber cut between two cities, say Chicago and Denver. This happens far more often than people realize. Construction crews take out a conduit, wildfire damages infrastructure, submarine cables, if you're going across an ocean, fail, hardware breaks, all sorts of things. Inside of the provider networks, the routing protocol is detected almost instantly. Routers change inside of that IGP, shortest path calculations using Dijkstra. It all just works. So maybe the traffic reroutes through Dallas or Salt Lake City or a different network entirely. At the same time, the regional traffic, the BGP advertisements change as well. Again, if you think of it from the postal analogy, if an airport in Japan closes and the planes can't land there, the Japanese postal system might tell the US postal system, you might want to land everything at airport A instead of airport B. Again, these networks receive these changes and independently recalculate, and they make their own routing decisions. And what's fascinating about the network reorganizing itself without this centralized controller is that's core to what we've been talking about. Again, back to the basic question. Given this packet, given this destination, given where this package is trying to go, where do we go next? What does the algorithm tell us? What does the policy tell us? What is the condition of the network? And I mean the roads or the actual fiber network tell us. Because routing is not just one master controller, one master computer telling everything where to go. It's thousands of systems sharing information based on what they can see and what they know, applying that policy, reacting to failures, and making the next best decision. And what's fascinating to me is just the exact same pattern that shows up in physical logistical systems too. Now we get into the packages part. A package delivery network does not require every warehouse, every aircraft, every sorting center, every delivery driver to understand the entire global system. Again, that'd be pretty impossible. Local facilities, just like local routers or local postmen, make local decisions. Regional hubs aggregate flows. National and international systems move volume across major transportation corridors. Final mile, or the actual delivery of the package, becomes detailed again. And it's those people that, take that package up to the front door that know the streets, the roads, the best way to get to your house or my house, the best way to avoid that traffic jam. At every level, the system balances detail and abstraction. Too much detail and the system doesn't scale. Too little detail and things don't get routed properly. So routing is just kind of an art and a science married together of finding the right level of detail and the right system. So it's just really wild how all this works. A postal hub doesn't need to know about your front door. It just needs which regional facility should handle the package next. A router doesn't need to know the whole internet. Just needs to know, do I send it to something I have a specific route for based upon an IGP? Or do I send it to that group of networks over there that have advertised it to me in BGP? And I know it'll get to Japan if I send it over there to those Japanese routers. And when those millions of small decisions are being made nearly instantaneously, all the time, it's just clearly magic. So once you start to see these routing decisions, you start noticing it everywhere. And once you understand internet routing deeply enough, physical logistics suddenly stops looking like trucks and warehouses and starts looking like another routing system solving the same underlying problems. It's classic, if you got a hammer, everything looks like a nail. Well, I'm a routing guy, so everything looks like routing to me. Which is exactly why logistics becomes so interesting to me. And we're finally there in this series to the packages part. How the items my daughter bought online really start to move to our front door. Atoms, not pixels. So when a package arrives in a warehouse, it enters a network that's constantly making, you guessed it, routing decisions, just like the internet does. And just like internet routing, there's almost never a single perfect path. There are trade-offs between cost, speed, capacity, labor, humans available, weather, fuel prices, transportation schedules, places to park the trucks, aircraft capacity, inventory placement, customer expectations, that policy, all sorts of things. At a high level, logistics systems are solving versions of something called the vehicle routing problem. Given a large set of destinations, vehicles, warehouses, packages, operational constraints, how do you move everything through the network, through the roads, through the warehouses, as efficiently as possible, just like routers do? And this becomes extraordinarily difficult at scale because physical systems add a different constraint that packet routing in the pixels world and the electrons world doesn't have. And that is packages occupy physical space. They have weight. They're atoms. Some cannot be stacked. Some require refrigeration. Some contain hazardous materials. Some require special handling or signatures. Some can't be delivered to certain states or certain regions or certain parts of the world. And unlike packets, packages almost always move in batches. You almost rarely see a package move from point A to point B by itself. And that moving in batches changes the optimization problem really dramatically. Remember, a router forwards packets independently. Every packet gets an independent decision. Every packet looks across those routing tables and figures out which way to go. But logistics systems contain something where they're constantly consolidating items together to maximize utilization. You want to fill that truck up. You want to fill up that container. You want to fill up that plane. You want to make sure things move. You want to fill up that local delivery truck. A single trailer or cargo aircraft may contain thousands of packages with different destinations, dimensions, priorities, delivery guarantees, which means every routing decision affects other routing decisions downstream at the same time. And the complexity just grows and grows and grows. This gets so much fun. What becomes really interesting is that the warehouses themselves begin behaving like distributed systems. Inside a modern warehouse or fulfillment center, software is coordinating almost everything continuously. Which worker picks which item, which doors are overloaded, which docks are used, which conveyor lanes are backing up, which shelves are running low, which outbound trailers are close to missing their departure windows, which forklifts are available, which robots are allowed to pick, which orders need prioritization, are all being tracked in real time, all the time. Even deciding where products physically sit inside the warehouse becomes an optimization problem. Fast-moving products are typically stored close to the packing stations to reduce walking time. Heavy items may require reinforced shelving or placed on the floor. Products frequently purchased together may be co-located to reduce picking complexity. Things you buy together should be near each other so people aren't running from one side of the warehouse to the other. If you haven't seen pictures of these large commerce warehouses with robots and conveyor belts and packages being picked and moved between humans and trucks, go check it out. Go online and search. It's really, really cool and wild and super fun to watch. But warehouses always have to think about congestion management in ways that look remarkably similar to computer networks. So imagine we're in the holiday season and one particular toy becomes wildly popular. If every unit of that toy sat on a single shelf in a single aisle, just imagine all the workers and robots that have to pile up into that location trying to grab that thing. Retrieval slows down, congestion increases, forklifts back up, throughput basically collapses. So modern warehouses often intentionally distribute inventory across multiple physical locations. The same toy might be stored in different shelves, different aisles, different warehouse zones, so multiple workers can retrieve it simultaneously without bottlenecks forming. And conceptually, almost identical to load balancing inside of a data center. You might recall load balancing is when requests come in, instead of hitting a single server or a single location in the data center, you distribute to multiple locations and have them all reply in parallel. Back in those earlier episodes, we talked about load balancers distributing those inbound requests across multiple servers running the same application or AI model. So instead of overwhelming that one machine, traffic gets spread and requests can be processed in parallel. Same thing with humans in warehouses. Warehouses are doing the same thing physically. Instead of routing every worker to one crowded shelf, we distribute the retrieval access across multiple locations and reduce congestion. And at some point, you realize warehouses are solving problems that look surprisingly similar to optimizations with inside computer systems. Frequency accessed pieces of computer information or inventory get positioned closer to where demand occurs, almost like hot data being placed near processor caches. And just like inside of computers, inside of warehouses, these layouts aren't static. During season demand, warehouses may reorganize inventory placement to maximize throughput. And not all logistics networks and not all warehouses are optimized for the same thing. Some third-party logistic providers, called 3PLs, specialize in lightweight, high-volume e-commerce fulfillment. Think like clothes and easy, lightweight things, where an entire factory is optimized around conveyor systems, barcode scanners, rapidly sorting lanes, robotic picking systems, small package throughput, all the little things we order. Others specialize in heavy freight, like furniture, industrial equipment, appliances. And in those facilities, they look really different. You get wider aisles, you get forklifts instead of conveyors, you've got to balance the pallets out where the things sit. You got to deal with trailer weight optimization to make sure the trailers are weighted properly. You've got to schedule docking systems to make sure the trucks back up to the docks when the heavy items are there. You have specialized lifting equipment. All of this becomes part of the cost of routing. Remember that cost idea, like how much does it cost me to move this packet? How much does it cost me to move this package? How much does it cost me to move these items? Sometimes it's policy, not shortest distance. Policy might be, is the forklift available to move the washer and dryer, which is a heavy item? Then there are the things logistical and logistics networks optimize for, which is international shipping. And this is where things sound eerily familiar to exterior routing or the border gateway protocol. So international logistics induces all sorts of new fun. Customs processing, bonded warehouses, import duties, ocean freight schedules, air cargo constraints, country-specific regulations, carrier agreements between organizations. A package moving internationally may not follow the geographically shortest route at all. Instead, it may get routed through a particular country because customs processing is faster, tariffs are cheaper, cargo capacity is available, or there's just contractual agreements that make moving that item cheaper. And at some point, international logistics starts looking a lot like internet routing policy. In both systems, the path that something takes is often shaped as much by economics and traffic engineering and policy as it is by just what's technically efficient. These are constantly adapting to failures and disruptions as well. Imagine logistics is always looking at failures and disruptions, just like internet routing is with routers and data centers and fiber cuts. Imagine a delivery truck halfway through its route when a major accident blocks a highway. I'm sure it happens all the time. Fleet management systems ingest this real-time traffic information continuously. Routing software might dynamically recompute portions of the route. We see this all the time on our GPSs, right? We're driving down the street, the GPS reroutes us because of an accident somewhere. So that means for a delivery truck, for that packages part, the delivery stops might get resequenced, alternate roads might get used, delivery windows get updated, and in some cases, packages might get even reassigned to different vehicles. They're moved over to another network or another city or another way to get there. If a fulfillment center becomes overloaded because of staffing shortages, people get sick, things happen, power outages or weather, shipments can get redirected to a secondary hub with spare capacity. Inventory originally intended for one city may get distributed somewhere else entirely. The physical world and the logical internet world are just so similar in so many regards. However, unlike packet routing, physical logistic failures tend to cascade operationally. What I mean by cascade is, think of this, a delayed aircraft affects truck schedules. A late truck affects dock assignments. Missed dock windows delay outbound trailers. That affects when humans need to load the trucks. which affects downstream sorting facilities and local delivery routes. Physical systems have this inertia because you're moving these atoms around instead of bits around over fiber. And because those atoms need to physically move, when they get backed up or moved or sorted or repackaged or rebunched differently, it becomes harder to recover and operationally a lot more expensive. And one of the most really wild and fascinating developments in modern logistics in inventory is something called pre-positioning. You hear about this all the time in e-commerce. So instead of shipping every item from one giant centralized warehouse, companies increasingly distribute inventory closer to the expected demand ahead of time. Pre-positioning. If the weather forecasts predict an increased demand in umbrellas in Southern California, inventory may already be staged there before the customers place the order. If forecasting systems predict increased demand for a given toy, you might pre-position those toys or those items, a piece of clothing, in a warehouse close to where you think people are going to want to buy it. This reduces delivery latency, transportation cost, while improving overall package network efficiency. And what's wild about this is this starts to look a lot like CDNs. We talked about this in a previous episode, content delivery networks. CDNs replicate data close to users, so requests don't have to repeatedly go all the way back to the data center. You might recall in a previous episode, I talked about when you load a web page, sometimes the images are actually much closer to you, but the application logic, the payment is in the data center. But the images, the buttons, the things that look and highlight the rest of the web page are on the CDN and they're closer to you. This is pre-positioning data. This is what we talked about a few episodes back, where things that are stored closest to your laptop and they don't need to get retrieved from the data center. So there's two types of content at the edge in this case. The edge for CDNs is internet traffic, and the edge for packages is regional warehouses and pre-positioning. In both systems, the network is no longer just routing efficiently. It's proactively shaping itself to reduce future routing costs. Because the more you can make routing happen quicker, the closer you can bring the packet or the package close to the end user, then you avoid the policy decisions, the possible reroutes, the fiber breaks, the truck breaking down, because guess what? You're traveling shorter distances. And that's really the deep idea underneath all of this. This idea of routing, going from point A to point B, having individual decisions made by postal carriers, sorting hubs, routers, data centers, is never actually solved. Maybe that's why I like it so much, because it's just this constantly evolving thing, evolving and adapting. The internet is constantly recalculating paths across failures, congestion, demand, data centers, policy, traffic engineering. Logistic networks for packages are doing the same thing with warehouses, trucks, aircraft, ports, labor shortages, weather, inventory placement. Pre-positioning. Different materials, pixels and packages. Same underlying problem at the end. Internet routing and package routing. Routing inside warehouses versus routing inside data centers. It's all fundamentally the same idea appearing over and over and over again at a planetary scale. It's a remarkable process happening billions of times every second of every day across the internet and across the physical world around us. And unless we stop and look, most of us never even notice it happening. It's just really, really cool. And it's so not surprising at all why I love routing so much. So thank you for listening to this latest episode of Pixels to Packages. I hope you enjoyed it as much as I did. I had a blast with this one. This one really used the concepts we talked about in episodes 1 to 5. So go give those a listen again if you missed something along the way. Also, do me a favor, subscribe and like to this podcast on your favorite podcasting platform and tell your friends. Always love to get more feedback and always love to hear about more people listening to the content we're producing here. Thank you again. Talk to you next episode.